This is a tokamak fusion reactor, humanity's best shot at unlimited clean energy, simulated in C++ using OpenGL. You've probably heard about fusion being the holy grail of energy, the same process that powers the sun, created here on Earth. In this video, I'm going to take you through the entire journey of building this thing from scratch, using real physics equations to simulate the behavior of plasma in fusion reactors. So, let's start with the plan. Simulating a fusion reactor has multiple crazy parts to it. First, we need to understand what we're actually building. Fusion is a process of smashing two light atomic nuclei together so hard that they merge into a heavier nucleus. And when they do, a tiny bit of mass, less than 1% of the total, disappears and converts into pure energy, according to Einstein's famous equation E equals mc squared. The c squared is the speed of light squared, a massive number, which means even a tiny amount of mass converts into an enormous amount of energy. This is literally the power source of stars. Here on Earth, we use deuterium and tritium, two heavy isotopes of hydrogen. When a deuterium nucleus and a tritium nucleus gets close enough and slam together, they fuse to create one helium-4 nucleus carrying 3.5 mega electron volts of energy. That's more than 17 million electron volts total from a single reaction. To put that in perspective, that's about 10 million times more energy per kilogram than burning gasoline. But here's the problem. Atomic nuclei are all positively charged, and positive charges repel each other. Like trying to push two magnets together at their north poles, they push back. To overcome this electric repulsion, you need to slam them together at insane speeds. And the only way to get atoms moving that fast is to heat them to 150 million degrees Celsius, 10 times hotter than the core of the sun. At these temperatures, matter doesn't exist as a solid, liquid, or even gas. It becomes plasma, a soup of positively charged ions and free electrons, all stripped apart and moving at ridiculous speeds. So we have this ultra-hot plasma where fusion can happen. But now we face the second problem. At 150 degrees, this plasma would instantly vaporize any material it touches. That's where the tokamak, a giant donut shape or torus, if you want to sound fancy, comes in. We use magnetic fields to trap the plasma in midair, keeping it away from the walls, while the fusion reactions happen inside. To simulate this properly, we need three main components: the tokamak geometry, the magnetic field system, and the particle physics. And since we want this to look awesome, we'll also need a GPU ray tracer to visualize everything accurately in real time. If this sounds a lot, don't worry, we'll break it down step by step. Let's start by creating the tokamak geometry. I begin by setting up OpenGL and creating a basic window with an orbit camera. Pretty easy stuff. Now, here's where it gets interesting. The tokamak isn't just a simple donut. The cross-section of the plasma, the shape we'd see when you slice through the donut, is actually a D-shape. It's elongated vertically and has this triangular deformation called triangularity. These shapes are crucial for plasma stability. So I create a tokamak geometry struct with all the parameters we need: major radius for the big donut ring, minor radius for the tube thickness, plasma elongation, and triangularity. Think of the equation as starting from the simplest possible shape, a circle of radius a, where r of theta equals a cosine of theta, and z of theta equals a sine of theta. That would describe a perfectly round plasma cross-section. The term kappa modifies only the vertical part. So z of theta equals k kappa sine of theta stretches the circle upward when kappa is more than 1, turning it into an elongated shape inside instead of a round one. The triangularity delta acts more subtly. Instead of changing the size directly, it slightly shifts the angle inside this cosine as theta plus delta sine of theta, because sine of theta is largest near the top and bottom of the plasma. This angular shift pushes those regions inward. So the whole formula is really just a controlled deformation of a circle. But here's the thing, we don't want to just draw this shape. We need to know at any point in 3D space, are we inside the plasma or outside of it? This is crucial for particle collision detection later. This is where signed distance functions come in. An SDF tells you the shortest distance from any point to a surface. For a simple sphere, it's trivial. But for a D-shaped torus, we need some modifications. I implement a custom SDF using Newton's method. The idea is, given a point in space, find the closest point on the plasma boundary curve, then measure the distance. The Newton iteration converges in just 3 steps, which is perfect for real-time graphics. Let me test this real quick. Perfect. Okay, so now we have our donut. How do we actually confine the plasma? Let's consider a charged particle having a mass m moving in velocity v in a magnetic field B. The force being exercised on it is the Lorentz force, Q times V times B. This tells us a lot of things. The magnetic force B is always perpendicular to the particle velocity, so the magnetic force will not exert any work on the particle. Since work is zero, the particle's energy stays constant. That's no good. A force perpendicular to the velocity cannot change speed, it only changes direction. But a continuous change of direction implies a curved trajectory. In a uniform magnetic field, this curvature turns out to be circular. Let's see why. Assuming a uniform magnetic field pointing to the z direction. Now we consider a particle with velocity v perpendicular to that field, say in the x direction. The magnetic force is then perpendicular to both v and b, causing the velocity vector to rotate continuously in the plane perpendicular to that field. In the uniform circular motion, the required centripetal force is mv squared over r, and the magnitude is absolute value of q times v times b. Since b is responsible for bending the trajectory, it provides the centripetal force, so it becomes mv squared over r. And now solving for the radius, m times v over q times b. And finally, for plasma at temperature T, the typical perpendicular velocity satisfies 1.5 m times v squared, which is almost Boltzmann's constant times the temperature. So v is approximately square root of 2 times Boltzmann constant times t over m. So the radius becomes root squared of 2kbt times t over q times b. This is called the alarm radius. The lower it gets, the particle gets bounded to the field line. The higher it is, the more it drifts towards the wall. Phew! With that out of the way, the question becomes, how do we design the actual fields to satisfy the Larmor radius condition? For that, we need two fields. A toroidal field, this wraps around the donut the long way, created by massive magnetic coils, and it provides the primary confinement. Second is the polyidal field, wraps around the tube cross-section, and it's created by the plasma current itself. When you combine these two fields, you get helical field lines, like a twisted spring going around the donut. These helical paths are what traps the particles. This is expressed by the radius of the toroidal field over the radius of the polyidal field. The toroidal field decreases with distance from the center axis following b proportional to 1 over r. Meanwhile, the polyidal field is more complex, created by the plasma current flowing through the torus. Now it's time to add particles in our simulation. I create a particle struct that stores position, velocity, mass, charge, and particle type. We're simulating deuterium and tritium, the fusion fuel, plus helium-4, that's the fusion product, and neutrons and electrons, etc., where each particle has different properties. Now, for the physics. We write the Lorentz force equation that takes the two velocity axes and the two force axes, and then outputs the cross product. Particles also experience the mirror force. This is a gradient force that pushes particles away from regions of stronger magnetic field. It's what helps keep particles from drifting into the wall. Okay, so I've got all the physics working. I initialized 500 particles with random positions and velocities, and I run the simulation. Perfect. With all the physics done, we can now add a third dimension. Our final goal is to simulate a reactor that looks like the real thing, as close as possible. For now, we'll need realistic lighting mechanics, and for that, we'll need to make a ray tracing file. So, what is ray tracing, and why do we need it for a fusion reactor? Traditional rendering works by taking 3D objects and projecting them into the screen as triangular shapes, and coloring the pixels. But fusion plasma isn't a solid object with a surface. The plasma at the hot core is white hot, the middle regions are orange, and the edges are deep red. We need to see through the plasma, with light accumulating as rays pass through different density regions. That's why we use ray tracing. Instead of rendering surfaces, we shoot rays from the camera through each pixel on the screen, march those rays through 3D space, and sample their plasma properties along the way. At each step, we ask how bright is the plasma and how dense it is. Then, we accumulate the emissions and absorptions as the ray travels through the volume. We can reuse the same SDF we built for particle collision detection. Remember that torus SDF function that tells us the distance to the plasma boundary. In ray tracing, we use that to march efficiently. Then, when we're outside the plasma, we can take big steps equals to the distance. When we're inside, we take small steps to sample that volume accurately. So, for each pixel, we generate a ray from the camera, march through space using the SDF for acceleration. When inside plasma, sample density and temperature at each step, accumulate color and opacity using volumetric rendering equations. Now the problem is that I'm doing all these calculations on my CPU, one particle at a time, with 10,000 particles, each needing magnetic field evaluations, force calculations, and position updates 60 times per second. My poor CPU would just melt. This is exactly why we need to switch from CPU to GPU, so I create a GPU compute shader that can process thousands of particles simultaneously. The compute shader kernel looks like this. Each thread handles one particle, we get the particle data, we calculate magnetic field at particle position, that's Lorentz force, and update velocity and position, and then we check plasma boundary collision. This should give me beautiful, smooth rendering of a plasma volume with realistic lighting and transparency. For now, the coolest part, actual fusion reactions. I check every frame for particles that are close enough and have enough kinetic energy. When fusion occurs, 1. Remove the DNT particles, create helium-4 particle moving in one direction, create a neutron moving in the opposite direction, create a bright fusion flash at that location, and add energy to our power output counter. And now, for the final result. And there you have it, a full fusion reactor simulation built from scratch using real physics equations. Before you go, I just want to say a massive thank you to everyone who's been watching, liking, and subscribing. It really helps me keep making these kinds of technical deep dives. Thank you so much for watching.